So we're going to continue with a couple more examples of finding confidence intervals for proportions. So our next example says, experimenters injected a growth hormone gene into thousands of carp eggs. Of the 400 carp that grew from these eggs, 20% incorporated the gene into their DNA. Calculate a 95% confidence interval for the proportion of carp that would incorporate the gene into their DNA. So first we need to find our p hat, which is going to be our 0.20. Okay. And then n, which is going to be 400. Then remember our formula for confidence intervals. Plugging in our information, we'll have 0.20 plus or minus, and then using our table, we go to 95% for our confidence interval, and we look for our critical score, which is 1.96. And we'll have 0.2 times 0.8 all over 400 underneath our square root. So in the calculator, we'll do 1.96 times the square root of 0.2 times 0.8 all over 400. And we're going to get 0.20 plus or minus 0.039. So our lower value is going to be 0.20 minus 0.039, which is 0.161. And our upper value is 0.20 plus 0.039, which is 0.239. Okay. And lastly, I just want to explain what our confidence interval means. So with 95% confidence, the proportion of all carp who have the gene in their DNA is between 0.161 and 0.239. It is important to understand the meaning of our confidence interval. So being able to write a sentence interpreting what your confidence interval will mean is a very important piece of this. Okay. And then our last example says, a December 2007 Gallup poll consisting of a random sample of 1,027 adults found that 17% had gambled on sports in the past 12 months. Find the 80% confidence interval for the proportion of all adults who gambled on sports. Interpret this interval and additionally state the margin of error in the study. So first we start with our p hat, which is going to be 0.17, and n, which is 1,027. And our confidence interval formula. So we'll have 0.17 plus or minus, and then going to our table, going to 80% for our confidence interval and looking at our critical score, we have 1.282, and we'll have 0.17 times 0.83 over 1,027 underneath our square root. Okay. Remember, the margin of error is this value that we add and subtract from our p hat. So 0.17 plus or minus, and then 1.282 times the square root of 0.17 times 0.83 over 1,027. It's going to give us 0.015. So 0.17 minus 0.015 is going to be 0.155, and 0.17 plus 0.015 is going to be 0.185. Okay, so again, if we write our sentence, we can say with 80% confidence, the proportion of all adults who gambled on sports is between 0.155 and 0.185. Next, we're going to talk about margin of error a little bit more. So sometimes we want to limit the margin of error in a study. So when we do that, the only thing we can control is the number of people we would include in our sample. So the more people included in a sample, the smaller margin of error. So if we can restrict the margin of error, we can determine our sample size. So our margin of error formula is that critical score times the square root of p hat times 1 minus p hat all over n. So if we worked backwards, we can use that formula to solve for n, which would be finding a sample size that would result in a specific margin of error. So that leaves us with n equals p hat times 1 minus p hat times the critical score divided by the margin of error squared. Okay. The one piece of information that we need here is p hat, which is based on sample size. So what we would do here is either use a value from a previous study. So if you were given on a previous sample size what p hat is, you would use that. If you're not given a previous p hat, we use 0.5 always. Okay. So we'll take a look at a couple examples. So a recent study indicated that 29% of women over age 55 were widows. How large a sample must one take to be 90% confident that the estimate is within 0.05 or 5% of the true proportion of women over age 55 who are widows? So we're going to use our formula, n equals p hat times 1 minus p hat, and then in parentheses our critical score divided by our margin of error squared. So we need to identify our information. So we know that the recent study indicated 29% were widows. So p hat is 0.29. Our critical score is based on our confidence. So if we want to be 90% confident, that would be 1.645. And then our margin of error comes from the 0.05. Okay. So plugging those values into our formula, we have 0.29 times 1 minus 0.29 times 1.645 over 0.05 squared. So plugging all of that into the calculator, get 222.87, which means 223 people would need to be in the sample. Okay. So we're going to look at the same example, but now we're going to go based off no estimate of a sample proportion, and we're going to see how that changes the sample size that we're going to need. So this time p hat is going to be 0.5. Our critical score is still 1.645, and our margin of error is still 0.05. So we're going to have 0.5 times 0.5, because 1 minus 0.5 is still 0.5, and they'll have 1.645 over 0.05 squared still. So we end up with 270.6, which means we would need 271 people in the sample. So we can see how not knowing a estimate of a sample proportion can drastically change the sample size needed. Whether the p hat is smaller or larger than 0.5 determines if we would need a larger or smaller sample size. The other thing is, when we are constructing our confidence intervals, the more confident we want to be that the population proportion is included in our interval, the wider the interval is going to be. That way we can make sure it is included. If we are less confident about the parameter being included, then we would have a smaller interval. So we want to keep that in mind when we are constructing our confidence intervals. If you have any questions over confidence intervals, solving for sample size, or even our table where we get our critical scores, please let me know.